Hi. Hello.
Yes.
Yeah. Okay, welcome back. Oh. Yeah, check.
For the lunch.
And
For the lunch.
okay. So welcome back on the second day. The registration and the reimbursement, if you have not done till now, please do it by just before lunch, because it will be closed after lunch. Okay. And we'll have a group photo just before lunch. Okay. So we start this session with a very interesting talk from Professor Srijan Kumar. And the talk is in advances in AI for web integrity. So Srijan is an assistant professor at College of Computing at Georgia Institute of Technology, GATEC. And he develops data science, machine learning, and AI solutions for pressing challenges of web safety and integrity. And his methods have been used in production at Flipkart, influenced Twitter's largest e-commerce, Twitter's birdwatch system, and taught at graduate level courses worldwide. And he has been named the Forbes 30 under 30 class of 2022, selected as a Kavli Fellow and a CRA Computing Innovation Mentor, and has received several awards, including the Facebook Faculty Award, Adobe Faculty Award, ACM CKDD Doctoral Dissertation Award, Dissertation Runner-Up to 2018, Larry S. David's Doctoral Dissertation Award 2018, and Best Paper Honorable Mention Award from WWW Conference. His research has been part of a documentary and covered in popular press, including CNN, The Wall Street Journal, Wired, and New York Magazine. He completed his postdoctoral training at Stanford University, received PhD in computer science from University of Maryland, College Park, and BTech from Indian Institute of Technology, Kharagpur. Thank you, Srijan, for coming. Please. Yeah.
Fraudsters, bad actors, malicious users, misinformation, and online hate speech threaten the safety, integrity, and well-being of users, communities, and platforms online. They pose one of the biggest threats. To public health, democracy, science, and the entire society. The problem is huge. Facebook estimates around 5% of its accounts, or a whopping 145 million accounts, to be fake. And Amazon estimates 300 million reviews to be fake on its platform. I am Srijan Kumar, and I direct the CLAUS lab, or the Computational Data Science Lab at Georgia Tech. And my students and I build AI, machine learning, and data science solutions to improve the safety, equity, and integrity of these online social media platforms. We develop graph neural network, multimodal learning, natural language processing, and adversarial machine learning techniques to detect what we call multi-X, to create multi-X detection models, where multi-X stands for multi-platform, multilingual, and multimodal content. In the domains of web safety and integrity, just like we are trying to catch bad actors are trying to evade the detection systems. Therefore, we create robust as well as accurate detection systems. Essentially, we model bad actor behavior as using adversarial machine learning and apply it on real-world large-scale data sets and systems to understand how some of the biggest deployed integrity solutions, such as those deployed at Facebook, Twitter, and so on, whether those are robust to bad actors, and how we can create the next generation of systems that are not only accurate, but are also robust. Third, we attribute the role that technology as well as humans have in exacerbating cyber harm. And finally, we create data-driven solutions to mitigate these online harms and create the next generation of platforms that are safe as well as usable. Let's start with detection. Imagine you are a social media platform and a user logs into your platform, and your job at that very moment is to identify whether this user is malicious or benign. You know this user's all previous interactions. You know all other users' all previous interactions, which includes all the posts that they have made, all the likes that they have done, and so on. How can you make a critical time-sensitive decision on whether the actor is good or bad? The same thing happens when you're trying to identify harmful content, looking at, let's say, identifying misinformation or online hate speech, and so on. Some of the biggest challenges today facing social media is that online harmful content is not just in English, but in fact is multilingual. Statistics show that 74% of data online is actually not in English. However, most of the work that we are doing today in the NLP natural language processing community is actually in English. So we asked in a recently published work, how accurate are non-English classifiers in identifying harmful content as compared to their equivalent English language classifiers? And think of all the misinformation or hate speech that you may have seen on social media or on WhatsApp that's in Hindi or whatever your local language is. While there's a lot of effort in identifying English language harmful content, there's not enough effort to identify harmful content in other languages. That's what this particular work is trying to establish. So first, we look at how we compare the performance of these English versus non-English language classifiers. And second, we develop models that overcome this disparity if there isn't. So we created this, there's no real data set that we could use. So we created our own data sets where we take content that's in English for various different tasks, including crisis humanitarian detection, essentially detecting when there's a disaster, fake news detection, and emotion detection. All of these data sets are reasonably sized, but they only have English content. So what we did was we created equivalent versions of these data sets in English as well as in 6 other languages using human translators as well as machine translation. So we did a lot of validation to ensure that the translations are accurate, stable, and people are able to say that both of these content are actually equivalent. And essentially what that means is that after we have created the data set, we have this content where each post has image as well as text, but now we have equivalent versions of this image and text pair, not just in English, but in 6 other languages. That includes Hindi, Chinese, French, Spanish, Portuguese, and a few more. And then what we did was we took the state-of-the-art classifiers, the natural language processing models that are multilingual, which means they work on all these on multiple languages, as well as language-specific classifiers such as Beto for Spanish. And then we compared the performance of these models on English, on detecting harmful content in English versus the equivalent harmful content that's in the other language. And what we found was very alarming. English language classifiers get an F1 score in the classification task at 0.65, while all the other languages have a reduced F1 score in the for the same equivalent detection task. The lowest one is actually in Hindi. So what that means is that there's a 21-point F1 score gap if you want to detect harmful content in English, and if the same harmful content is written in Hindi, the machine learning models would not be as accurate and would make a lot of mistakes. That highlights that there's a disparity, and this disparity needs to be fixed. So we try to fix that using one particular solution, which we call is multimodality. With multimodality, we are trying to create these late fusion-based multimodal classifiers, which are models that use not just the text, but also the images whenever they are available to do this classification. So essentially, you have the text, which is encoded using an NLP model called a BERT model, and you have the image that's encoded using a VGG16, which is a very standard image encoding model that's fused together and then used for classification into whatever the target categories are. And we asked, now that this multimodal content is there, which is the text along with other type of data, does it help improve the performance of the model? And what we saw was that indeed there's an improvement across the board. All the languages improve. The performance in all the languages improves when you're using images. But and in English, there's an improvement of 5% on average. But in non-English, there's an improvement of around 11.5%, so more than doubles. What that means is that solely using text is not sufficient to make accurate detections, accurate classifications. But when you have additional metadata, when you have additional information, that helps all the languages, but it helps the languages on which the models are not performing well more than it does English. So essentially, we gave one example of trying to bridge this gap. But in my opinion, there's a huge open area of research where people are just getting started to study these multilinguality, to study equivalent content in various languages, and trying to improve not just English language models, but other models. I'm sure all of you have come across, have been following the great buzz that's there in generative AI with ChatGPT and all the text-to-image and image content generators and so on. I believe in the next few months, even if not the next few years, all of these generative models will have a lot of multilingual capabilities. So you'll be able to say something in Hindi or your local language, and that will be able to create. You'll be able to create responses, and you'll be able to create multimodal content as well. So I think it's an area that's ripe for disruption, and multimodal, multilingual content is something that is super awesome. However, we have other solutions. We don't just have to rely on text or images, but in fact, some of the biggest advancements that we have seen and we have made is by using graph-based data. Here, I'm representing social media interactions or e-commerce interactions or any interaction as a temporal interaction graph. So temporal interaction graphs are an incredibly powerful and a super flexible way of encoding time-evolving relationships. Here, in an e-commerce setting, user purchases an item. Whenever that happens, we can represent the user as a user node in a graph, item as an item node in a graph, and the interaction as an interaction edge between the user and the item. And each interaction edge is associated with a timestamp and a feature vector. And as time goes by, more user nodes, more item nodes, and more interaction edges are created between users to represent how the graph is evolving. Now, you can take any sort of data that you have. There is a way in which you can represent that as a graph. And why are graphs important? Well, using graphs, you don't only have what the content is or what the individual modality, individual feature is, but you also are able to encode the relationships between entities. And that is something that really improves the performance. Graph neural networks, some of you, has anyone heard of graph neural networks in the audience? Okay, I see a lot of hands. Okay, that's great. So graph neural networks are actually one of the biggest and the hottest topics in machine learning these days, because people did a lot of work in computer vision for deep learning, then came text, and now people are getting super excited about graphs because you're able to leverage information, you're able to leverage content from various different entities and combine everything together. So this work that I'm talking about is one of the first models that is able to generate graph-based models, graph neural network models on temporal graphs, which is where the graph is evolving over time. And what we want to do is that given a temporal graph as input, typically what would happen is that you are given a graph and you would generate these what are called node embeddings, which means each of these user and item nodes would be represented as a k-dimensional vector in a would be represented as a point in a k-dimensional embedding space. Instead, since the graph is evolving over time, what we want is for these embeddings to also evolve over time, such that it creates these embedding trajectories. We call these dynamic embedding trajectories that encode how the graph has evolved, and you now know how these embeddings have evolved over time. And the model that we create that is able to learn these embeddings is called Jody. Very quickly, Jody stands for Joint Dynamic Interaction Embeddings. It's a KDD paper when I was that was published when I was doing a postdoc at Stanford with Professor Yuri Leskovich. And this Jody model is has two major components. It's a mutually recursive recurrent neural network framework, which has an update component and a project component. I'll very quickly go over what the components are, just to give you a high-level flavor of these. So the goal of the update component is to learn these embeddings, is to update the node embeddings after two nodes have interacted with each other. So when a user interacts with an item, so let's say you know from your log of the data that the user node, this user has purchased this item. After the interaction has happened, what the update component does is it updates the user embedding from the previous embedding to the new, and the item embedding from the previous embedding to the new. And how it does that is by using these user RNNs and the item RNN. So the user RNN updates the user embedding by taking the item embedding as input, while the item RNN updates the item embedding by taking the user embedding as input. And when that happens, you are able to generate these embeddings after the interaction. The project component forecasts these embeddings into the future. So it's able to forecast embeddings even when there are no interactions. And the main idea here is that if you have an embedding at any time, you can forecast where the embedding is going to be at any future time point. The way we do that is by essentially taking the core technology that powers Google Maps, and that's called Kalman filters, or at least the initial version of Google Maps. You know where the embeddings, you know how the embedding has evolved. So essentially you get its trajectory, and you can essentially forecast that trajectory into the future. The key idea being that if you want to forecast in very near term, then the embedding will not change a lot. But if you update the embedding, if you want to forecast the embedding at a very, very long future time point, then the embedding can change a lot. So to encode that, we created a projection operation that is able to generate these embeddings at any future time point. The model's trained, not going into the details, but we can use these user and item embeddings to predict and detect bad actors on social media. So we created multiple data sets. We released 2 new data sets as well. And Jody model outperforms all the existing baselines by over 12%. What got me super excited was a year after we released Jody, Facebook released a very similar model called TIEs, which stands for Temporal Interaction Embeddings. And they use it in production to identify ad payment fraud, fake accounts, and misinformation content. What this shows is that graph neural network-based models can be super scalable and can be applied to solve real-world platform integrity tasks and other tasks as well, such as recommendation systems, such as creating state-of-the-art recommendation systems. Shortly thereafter, folks at Twitter created temporal graph networks, which has essentially now become the baseline for all future research. And Twitter also uses TGNs for solving integrity tasks. So TGNs are actually generalization of Jody and various other models. And the reason I'm giving these examples is to show that these models are not just theoretical. It doesn't, like, we write great papers out of it, but it also has a lot of practical importance. People are actually using these platforms to solve real-world problems. In the last few minutes, in this particular section, I talked about two different types of models that can be used to detect harmful content. One was multilingual and multimodal. And then I gave a very generic model called Jody, which was graph-based. However, one of the biggest challenges in platform integrity is that even though you create the best, the state-of-the-art, the greatest models to detect bad actors and deploy it on your platform, it's just a matter of time, typically a few weeks, few months, till bad actors are able to find ways to fool these detection systems, to change their behavior, to adapt their how they are writing things and who they are connecting with, so that they go undetected for a longer time. That's essentially a cat and mouse game between the platforms that are trying to detect the bad actors and the bad actors that are trying to evade the detection systems. So far, all platform integrity solutions are very reactive, which means the bad actors change their behavior. The platforms wait for these systems to their performance to go down. Then they retrain their model, and then the platform the performance goes up again. However, that of course is not ideal. That is very reactive. And what we are doing is creating some of the first proactive solutions to create not just accurate, but also robust detection systems. And the way we are doing that is by understanding by first benchmarking how robust these systems are against adversarial manipulation. So what we do is we act as bad actors. So we take, in a sandbox setting, we model how, if I was a bad actor, how would I change my behavior to fool these detection systems? And the reason we do that is if we are able to identify these weak points, these vulnerabilities in these detection systems, we'll be able to patch these detection systems well in advance before deployment. So we created, with that idea in mind, we created one of the first solutions to identify how adversaries will manipulate their behavior to fool some of the state-of-the-art detection models, including the TIES model that I just told you about, that's deployed at Facebook. And in fact, what we found was that even with very simple manipulations, bad actors are able to fool the Facebook TIES detection system 1 out of 4 times. Recall that that's an in-production system. What we are showing is that if bad actors changes their behavior very slightly, they will not get caught 25% of the times. That's super high failure rate. If anyone is familiar with cybersecurity domain, even a 1% failure rate is super high. And this is 25% failure rate, which is quite low. Facebook knows this. This work was funded by Facebook through a faculty award. They're well aware of these shortcomings, and I hope that they are working on fixing those. We also looked at of graph-based recommender systems, because again, in these web social media domains, bad actors are trying to manipulate a lot of systems, including the recommender systems, so that their content, their harmful content, reaches a lot of people. Very quickly, what we showed very recently at an ACMC-IKM paper just 2 months ago is that by making very minor perturbations to the data, the recommendations of all the users changes drastically. So here, recall this graph, which was the graph between users and items, and we are training recommendation systems. We are training the prediction systems on these graphs using models like Jody and TIES and others. We asked 2 research questions in this particular book. How stable are recommendations when the training data, when these interactions are not exactly the same, but there are minor perturbations, which means if I decide to click something or not click something, that would create certain perturbations. We asked how stable are these recommendation systems to these minor insignificant perturbations. And second, we asked whether the impact is uniform across all the users. So we created a novel framework called Casper to essentially study this model sensitivity. So the idea is that if you have, let's say, 3 users who click on various different items at different time point or purchase different items at different time point, the way recommendation systems are trained is by taking this training data, taking these clicks as training data, training the recommendation model, and using the recommendation model to serve recommendations until the next time the model is trained, let's say after a month or a week. What we are saying is that if one user decided not to click on an item, what would be the change in the recommendation systems? And that's important because users are fickle. You don't want these models to be very sensitive to these minor insignificant perturbations, because you can have millions of training data points in your data set. So we compare the recommendations when a perturbation is present and when a perturbation is not present. And what we find is that even changing one training data point among millions of training data points reduces the stability of the model, which means the recommendations of not just that user, but everyone else changes. Now imagine the implications of that. If I decide to click on a Facebook article or a YouTube video, or I don't, that changes the recommendations of everyone else in the room. That shows that deep learning or state-of-the-art recommendation systems are actually quite unstable, even to minor perturbations. This is showing that if the model was stable, it would get a rank bias overlap, which you can think about as a stability metric of 1. But various different deep learning based models, including the Jody model, which I talked about, are actually quite unstable. They have a lower rank biased overlap, or the stability metric. And what this is showing is that even one random perturbation changes the recommendations of everyone. We have follow-up work where we have created solutions for that, where we are essentially creating adversarial training mechanisms that are able to take this training data and create recommendation systems that are accurate, but also stable. So essentially, we are trying to increase this rank biased overlap score for these models. What was alarming for us, though, was that the impact is not uniform across all the users. MRR is a standard metric that's used to identify how stable, how accurate recommendations are. And what we see is that for the users for which the model is already highly stable, highly accurate, it's also more stable. While for users for which the model is low, has low performance, it's also less stable. What that means is there's a disparity, again, between high MRR users and low MRR users, showing that these instabilities are impacting users for which the platform is already not making very accurate predictions. Nilay, sir, how much time do I have? Okay, all right. So 7 minutes, that's more than sufficient for me to talk a bit about some of the mitigation strategies that we have developed. We also have developed attribution strategies, but I'm not going into the details. I'm not speaking about that today. So I joined Georgia Tech in January of 2020. And in March 2020, because of the pandemic, everything went online. I'm still trying to figure out, which are the good Indian restaurants, where's good coffee, and so on. Still apartment hunting, but then everything went wild. And while there was a lot of chaos in the real world, there's also a lot of chaos going on in the online social media, online world. There's so much misinformation about how taking garlic could cure COVID-19, how 5G towers were responsible for spreading COVID, how Bill Gates is the mastermind and orchestrating all of this. And I'm sure everyone has their own favorite conspiracy theory and misinformation about COVID-19. And I had been studying misinformation for quite some time before the pandemic. So when the pandemic occurred, we started doing a lot of projects trying to understand how misinformation is spreading, who they are targeting, and what is the real world impact of that. We just very recently, just a couple of months ago, we got a grant from CDC, which is the Center for Disease Control and Prevention in the US, to study the impact of online misinformation on real world physical violence. So that project, we are super excited about it. We are collaborating with Anti-Defamation League and various other on-the-ground partners to study how, essentially, if I see some misinformation about a specific racial or ethnic or certain type of people, will I be more likely to engage in online or physical harassment against them? And what are the solutions that we can develop? So essentially, I'm saying that to say how how misinformation has real world impact. So we did a lot of analysis to study how misinformation spreads across platforms. So how misinformation starts in one platform and spreads on others. And what we found was that when you are looking at misinformation spread specifically on Twitter, while misinformation is spreading on Twitter, a lot of people are also countering misinformation on Twitter. Those are organizations, but also ordinary users. What we found for the first time was that almost all the countering messages, 96% of all countering messages, in fact, are from non-experts. So people like you and me, we are not journalists, we are not healthcare professionals, but ordinary users are the ones who are actually countering misinformation when that's spreading online. And we did a lot of statistical analysis to show that even speaking up, even a single countering message can reduce the spread of misinformation and equivalently hate speech as well online. So my advice is, if you see some misinformation, speak up, because that can actually and statistically reduce misinformation spread on these platforms. These are just some examples. And this work actually influenced Twitter's Birdwatch. And we also have some other work that's now currently being deployed on Wikipedia. Let me wrap up. Most of the work, or almost all the work that I spoke about today is thanks to my students, postdocs, and undergrad master students at Georgia Tech, and the sponsors as well. We also have openings for postdocs and PhDs. So if you are interested, come talk to me. So today I spoke about advances in AI for web integrity. I covered various different models for detection, robustness, and mitigation. And with that, I'll be happy to take any questions.
Time for
Yeah. Hello, sir. So my first question is, in that multimodal that you are saying in the first part, so when you are taking two representations, one is from image and one is from text, how you are fusing them? I mean, it's simple concatenation, or you are...
Yeah, so good question. So multimodal, so we used a late fusion model, and it's very standard. We didn't innovate anything on that. That just takes the image representation, text representation, concatenates it. And of course, the entire thing is trained, but yeah, the concatenation is the fusion.
Okay. And the second question is about Jody. So as you are saying, it's a temporal neural and temporal graph where you are applying graph neural network. So I was thinking, if we can use this multimodal information of items and users also on top of graph neural network. So suppose we have some node embedding we're getting from graph neural network, and we again fuse the other kind of information into it. What do you think? It will help in the final accuracy?
Definitely. Yeah, I think having initial metadata always helps. So when you're initializing the node embeddings, you can initialize, instead of randomly initializing, it always helps to initialize using some sort of feature vector. And if you have multimodal information, or if you have any sort of information and you use that to initialize, it definitely always outperforms random initialization. You also have features, you can also have multimodal or any sort of features in the interaction edges itself. That can also be taken as input when you're training these embeddings. So yes, I think, yeah.
Okay, thank you.
There's a question over here, and back over there.
Hi, thanks for the great talk. So I had a question in the section where you are showing that in your work, like you are trying to prevent impact from individual actions taken by a user in recommender systems. So that might prevent the system from picking up on new types of items or new things that come up on the marketplace, let's say marketplace. So those might get slowed down, right, when new things start happening.
So that doesn't, so these perturbations, when they are happening, they do not impact the quality of the, they do not impact the high level metrics that are used to identify, to measure how accurate these recommender systems are. So what you are saying does not actually happen, because these perturbations don't, it's one perturbation, one click that's either added or deleted or replaced among millions of clicks, right? So the impact should be very, very small.
Right, but that is in the large scale. So let's say if you are looking at recommendation for individual systems that are just coming up and does not exist in the system. So they will take more time to get picked up by the recommender system only when many people have discovered that item by themselves, and then the recommender system will start to think that as a valid set of actions.
Right. So you're talking about cold start. So cold start users or cold start items. These perturbations do impact cold start users and cold start items more. And that is exactly what this plot was, this disparity plot that I showed, where you had high MRR users and low MRR users. The same thing exists for low MRR items as well. So essentially, yeah. So here, this low MRR users are more likely to be cold start users. High MRR users are users that have been around on the platform for a longer time. So the model has more training data and therefore higher prediction performance. So yes, cold start does impact these performances, and essentially the perturbation impacts these cold start users and items more. Yes.
Thank you.
So yeah, thanks, Srijan.
Yeah, I'll just close this.
Thanks, Srijan. Thank you for coming. Professor Srivastava is an associate professor in the computer science department at Rice University. He is also the founder and CEO of Third Eye Corporation, a company that is democratizing AI to commodity hardware through software innovations. His broad research interest includes probabilistic algorithms for resource-frugal deep learning. In 2018, Science News named him one of the top 10 scientists under 40 to watch. He is the recipient of National Science Foundation Career Award, a Young Investigator Award for the Air Force Office at Scientific Research, a Machine Learning Research Award from Amazon, a Data Science Research Award from Adobe. He has won numerous paper awards, including the Best Paper Award at NIPS 2014, MLSys 2022, and the most reproducible paper at Sigma 2019. His work on efficient machine learning technologies on CPUs have been covered by popular press, including Wall Street Journal, New York Times, TechCrunch, NDTV, what is this? And Engadget, Arts Techna, etc. Yeah. Thank you for coming.
Thank you everyone for coming. It's always a pleasure to interact with the young minds. So I'm going to talk about something that I have been working for about 7-8 years now, and which I think is a new way of training and inference with AI, especially because the problems in AI has reached a point. And I'll also start with some motivation. So I want to start with the paper that was by Google in 2017. And this paper they were trying to train some natural NLP models, right? And they were training about 100 billion parameter model back in 2017. And thing to note there was the corpus also had about 100 billion words. Okay. So the abstract of the paper says that we needed this model size to absorb to model the variations in the data. The data has about 100 billion words, and I needed about 100 billion parameters to understand all of those. In the same paper, they said that, well, this is not our ultimate goal because we have a data set that has about 1 trillion words, right? So like a humongous corpus. And then they were also saying it is our ambition to train 1 trillion parameter model on the 1 trillion word corpus. And this is the line from the abstract that says model capacity is critical for absorbing the vast quantities of knowledge. Okay. So what is going on, and it's also evident if you just follow what is happening in the AI world. If you look at some of the best performing models, obviously some of them are transformers, a mix, MLP mixers, a whole bunch of things. But there's one thing common, that the number of parameters has been just going up. And I think this paper very nicely summarizes why. And if you're from an information theoretic background, there is a very easy information theoretic argument that model size will continue to increase. So imagine I want to now build a question answering system, a system which is capable of taking any question and producing an answer. Now, okay, enough of the machine learning. What you're giving me is a program that takes an input question and outputs an answer. So it's a function, right? And it doesn't matter whether it's a neural network or whatever you want to call it. If there are enough variations in the question and enough variations in the answer, the memory footprint of whatever function you're giving me cannot be small, period. That's information theory. What it means is that if we are looking for a very complex task, a variety of input being mapped to a variety of outputs, if we are looking for something like that, the model capacity cannot be small. That's basic information theory. In fact, it's also the other way around. If somebody gives you a very small model and say, hey, look, here is a small model that will solve your purpose, most likely the task is not complex. There is not enough to memorize in the task. There's not enough variation. It works both ways. So model size has to increase because our ambitions in AI is increasing. Now, here is another thing, and I'm more or less summarizing what I've been observing over the past, let's say, decade in AI. I will also argue that the architectures are getting simplified more and more. So there were a lot of talks about recurrent neural network LSTMs before, and then there was this paper in 2017 that said attention is all you need. And pretty much now we are in a state where everything that you can do with LSTMs or RNNs, you can do with attention. And what you can do with attention, probably LSTMs, RNNs, fell short of them, what they could achieve. Starting like 2 years back, even the need of convolution is now in question, right? There are papers and, we have worked in the seismic imaging with some of the oil companies, but it's also, people are now using transformer kind of architectures and getting equivalent performance with convolutions. So even convolutions maybe are not needed, right? Now, there are even papers that talk about even attentions are not needed, right? There is something called MLP mixers, which is more or less like, multi-layer perceptrons. Then there is something called synthesizer, which was again a paper by Google. We have worked on this paper called Pair Connect, where you were able to use pairwise embeddings to even get similar results at transformers. And this is going to happen, right? I mean, what people are realizing more and more often, in fact, there are papers that seem to point towards that model size is the only thing that matters. Architectures do not matter, whether it's convolution, transformers, or something that does not matter. So if you're hoping that there's something magical about transformer or something magical about convolutions, maybe not, because you could achieve similar results with something else too. And this is a good news, because I will say that architectures are getting simplified. In fact, if you ask the question, what is the most complex model that is out there? Obviously, in recommendation system, I think Facebook reported a model which is 12 trillion parameter model, and it's mostly fully connected. So to summarize, I will say that, like to solve a variety of AI tasks, anything reasonable and big is all you need. And actually what is driving the AI revolution is smart people, right? It's they call it PhD descent instead of a gradient descent. It's basically a bunch of PhDs thinking about what is the best way to solve this problem, what is the best architecture, and then they refine it. It's not a gradient descent, it's a PhD descent, they call it. So smart engineers are driving the AI revolution. What? There was a PhD ascent. Yeah, I think you call it should be an asset, right? Not a descent. So, I mean, again, like now, I know there has been talk about, like the AGI, artificial general intelligence. But even today, let's say you go and talk with two people doing AI, right? So let's say you talk with somebody who works in recommendation systems or NLP, and talk with someone who deals with, let's say, tabular data set, time series forecasting, right? And when you talk with them, it seems like they are speaking two different languages. One will talk about embeddings, transformers, blah, blah, blah. Other will talk about like trees, boosted decision trees and stuff. And in fact, the feature engineering processing seems like from a different world, right? So forget about AGI. What I think is what we need is even to simplify the process of AI, because every AI becomes a unique stuff, right? It's not very repetitive. So why is this an issue? To solve n problems, we need n specialized teams, right? This is, I mean, as we know, big go n, it doesn't scale, right? If with n people, I can only solve n problems. Whereas the whole point of AI was there's this one AI that will solve all the problems. And now we are still stuck in a loop where we need n people to solve n problems, right? And again, like it's slow and costly to validate a hypothesis with unpredictable return on investment. So let's say if you're a business leader, let's say you're trying to run an e-commerce company and you are like, okay, should I employ NLP? Now to answer that question, you first have to hire a team of people who knows NLP. You have to give them the infrastructure, which are likely expensive. Then they are going to take like 6 to 7 months of coding and development efforts. And after a while, they will come up to you and say, you know what? The answer is negative. It doesn't affect our business. And this is basically, you don't know what to do next, because what you did was a very specialized thing for a very specialized hypothesis. And if the answer is negative, you already paid the cost, right? So this is why there is a lot of talks about the return of investment in AI is very unpredictable, and many times you don't get the return on investment. So if we can simplify this AI with like sort of a, what I want to call it like a universal AI, in which if you have like, you basically have an AI where you tell AI, okay, you know what, my problem is recommendation. And the same AI works for NLP, the same AI works for tabular classification, the same AI works for forecasting, so on and so forth, then I think it will have a lot of impact even in the business world. It will bridge a lot of gaps. It will lead to a much larger adoption of AI and less fear about like the unpredictability of AI. And obviously, like I didn't mention about the infrastructure, the costs of GPUs are high, the chip shortage. So, I mean, again, like, so for example, if you have like, I can solve all problem just with like one AI and it's more or less production ready, that is something that a lot of industry will want. So this is what we are also like, I mean, I'm also involved as a part of Third AI. So this is what we are working towards, and I'll talk about how is that even possible. So we can now at this point of time, create a high level an AI with a high level of details. You just have to tell the AI what the data is, and data can be heterogeneous, multimodal, and this AI gets better with more data, and there is not much need of feature engineering or handholding, and you will get some of the state-of-the-art results. So I'm showing you two code snippets. One is basically trying to do a temporal classification of a sequential modeling of movie recommendations. So this is a Netflix problem and it has a sequential modeling. And this is your NLP text classifier, and the function signature more or less looks the same. As you can see, everything is auto-tuned, so you don't have to worry about what is the model or what are the hyperparameters, and it works out of the box and will give you the state-of-the-art result. Can something like this be possible? And if yes, how are we going to achieve this? So I will say with what is happening, right? The model size is increasing. You can train, if you can train really large models, that's mostly what is all you need. With that, it's kind of possible, right? I mean, so we are seeing the architectures are unifying. So it doesn't matter whether you are solving vision or NLP or something else, you should probably use one sort of an architecture, but it has to be giant, a large neural network. So what is a hurdle? I'll say the hurdle is the scale. And again, like I'm a scale guy. To me, if I can make training large neural network efficient, that solves a lot of AI problems. And that is what I'm going to show you how there are certain ideas that can do that very efficiently. And I think to achieve this universal AI, the bottleneck is precisely this. You need to be able to train very large networks with hundreds of millions to billions of parameters without requiring expensive infrastructure or expensive, engineering. And if we can achieve that, then we are very close to this. In fact, this is how the reason why we could do it at Third AI is you can actually run these on your CPUs, on your desktops, and they can train 100 millions to billion parameter models on your desktops. And this is the bottleneck that we eliminate using algorithms. And I'm now going to delve a little bit into the algorithmic details and how we do it. So just to wrap it up, training time and cost drives AI innovation. Everything is a model search, right? If you think about it this way, right? So for example, if you're looking for efficient inference, I want a model that can be deployed on a mobile. It's a model search for a cheaper model with good accuracy. It's still a model search, right? I want a model with the best accuracy. It's still a model search that falls within the limits of what I can define and train that has the best accuracy. And the way currently it's done is not very different from try, fail, try again until you get a success. Look at who is winning the AI race. There are teams like, the big companies, as we speak, there are teams who are constantly thinking about what hypotheses should I validate in the evening such that I know whether it works or not, right? And your capability to create a hypothesis and validate hypotheses is the single most important factor in this AI innovation. So if I can give you a capability where you can imagine a hypothesis and validate it by evening versus validate it in 2 weeks, I have cut down the cost. I have made AI progress 14x faster. And again, the community also recognizes that. So the 2021 ACM Turing Award was actually given to people who developed linear algebra libraries. Because if you look at all the acceleration in deep learning, why we could train convolution neural networks and all these fasters using either GPUs or CPUs is because I could do matrix operations very fast, which were actually the work done by several folks back around in several decades back. And we are essentially leveraging. In fact, to me, one of the biggest realization in machine learning was most of the machine learning process can be written as dense matrix multiplication, and dense matrix multiplication can be made faster. And all the advances that has been done in dense matrix multiplication comes handy in accelerating AI. However, we are seeing another wall. In fact, this is an article from IEEE Spectrum that is calling deep learning's diminishing return. So just extrapolating this fact, you need larger models to get to the better accuracy, but training larger models with larger data is expensive. They did some back of the envelope calculations, and there are two things that comes up. Is to half the error rate, you can expect to need more than 500 times the computational resources. And essentially that is also translate literally linearly in the amount of carbon footprint that is burned. And the number starts to look pretty worse. It's like, if you want to reach this bar, which is basically the bar that industries want to reach, we are looking at the carbon footprint, which is by whatever the New York City takes in 1 month, that will become an equivalent of a carbon footprint if we extrapolate this in the future. So what is the workaround? Well, there is this 2016 New York Times article that was talking about the ends of Moore's law, in which they said that, well, as the engineering and the hardware progress has slowed down, the new ideas are going to essentially come from human creativity. So we are going to revisit and think about what are very different ways to solve the script problem, right? So getting a little bit into like the technical details. So how many of you know the backpropagation algorithm? Neural networks backpropagation algorithm, right? I mean, I would assume everybody knows that. So in a backpropagation, what happens is you are shown a pattern, and then you take this pattern, compute some activations or a new representation towards a hidden layer, and then you go to an output layer which tells you whether this is a cat or another object, right? And then you compute an error and you backpropagate. That is the standard way of training neural networks. And the realization is you could write this as matrix multiplication, which has resulted into a lot of advances in AI. So now I want you to imagine that this is a billion parameter network, okay? So this is a billion parameter network and it has been trained for a while. Now you show it an image of a cat, and then the image of the cat now go and hits a billion parameters. So there are a billion floating point operations to get to an output. And once you see an output, you see an error, you do another billion floating point operation to update the parameters, okay? Now it turns out, first of all, you should notice that if you are using ReLU activation, ReLU is computing certain activation but not using it. So for example, if this falls below a threshold, it will be / never used. So you are doing 50% of extra work and never using it, okay? Now it goes to an extreme. In this case, if you do the gradient descent, you will find that the updates follow a power law. So essentially, only 1 to 2% of the updates will be significant, as in 99.9% of the updates will be like 0.0001. So if you look at what is the update on the particular parameter, it will be like 0.0001. If it's a very big network. In fact, I can show you some graphs that we did on GPT-3. 99% of the things are sparse. It is never used. On the top of it, people will come and say, you know what, precisions don't matter, let's quantize. So what is happening now on some of the popular packages, including TensorFlow, PyTorch, you name it, in fact, every acceleration out there, you do billions of floating point operation. And if you quantize it, you essentially are only updating few hundred to 1,000 parameters. Rest updates are all washed away. To me, that's quite wasteful. Obviously, you will need a GPU because there are still 2 billion parameter operations, and they are done in a way that they are calculating a lot of zeros. In fact, there is a saying that we pay AWS a lot of money for calculating zeros, right? Because, at the end of the day, you are doing that operation, you pay per compute, but you never use that. So the point to ponder here is, we do it efficiently, obviously, right? I mean, the question is, how can we do it efficiently? So the answer is yes, and I'll give you a brief, rough sketch of the algorithm. But things to note here is that we are going to use a specific term called sparsity. So we are going to make the update sparse. But sparsity is an overloaded word. Remember, if you are talking about static sparsity, you are saying that my model is small. You're throwing away parameters. You're saying that, well, out of this million or a billion parameter, I don't need 90% of them. That's like reducing the model size. It goes against what we have seen in the first slide, right? You cannot have a small model. So static sparsity is not going to work. Low rank, again, low rank will also not work because low rank also does the same thing. It reduces the number of effective parameters. What we are going to do is something different. It's a dynamic sparsity. So what I will say is, yes, there are billion parameters in my network, but on every input, the parameters that I'm going to use is sparse. So for cats, I'll probably use this set of parameters. For a signal, I'll use traffic signal, I'll use some other parts of the network. I will use all parts of the network on the data set, but for any given input, the amount of work I'm doing will be very small. And how we are going to materialize will be a different story, but this is how we are going to train a neural network. Instead of we taking an image of a cat and hitting all the billion parameters to compute the output, we are going to take the image, we'll figure out only very few parameters, and I'll show you how, and then we'll compute the output, and this way we'll reduce a lot of calculations. So instead of doing billion floating point operations, I'm going to get away with, let's say, few thousands. And this is what we are calling dynamic sparsity. And it's, I mean, again, like if you want to think about in many ways, like let's say the world has a lot of concepts. So the concepts could be eyes, nose, ears, wheels, antennas, blah, blah, blah. right? I, as a face, is sparse in those concepts because I don't have wheels. I don't have antennas. I have nose, eyes, ears. A bus is also sparse in that concept, right? A bus does not have nose, eyes, and ears, but it has wheels. It has steering. It has something else, right? So every input is sparse in terms of the number of concepts, but the number of concepts are big. So you need a lot of parameters, okay? How are we going to do this? So imagine, in this case, let's say I give you an oracle. So the oracle somehow looks at the image and tell you exactly the parameters that needs to be updated, that are going to be significant, let's say after quantization or something. If I give you that, then your problem is solved. Because you know, all of these parameters, let's say, are not updated. I don't even have to use it, I'll throw away, at least for this given input. So on this input, an oracle comes and tells me, hey, look, these are the only parameters you need to worry about, and there are 1,000 of them. Then I will only forward propagate my input on those 1,000 parameters and back propagate on those 1,000, and that's as good as doing the whole work. But I need that oracle, right? And that oracle, no wonder, is a search oracle. So the key puzzle here is, how do we identify parameters relevant to a given input beforehand? I don't know what input I'm getting. I'm getting a cat or a traffic signal or dog. How do I identify that? But that sounds like a puzzle that we have solved. Search. When you type a query, Rice University Computer Science, your query doesn't go and hit all the web pages in the world to figure out which web page to show you. The web page is indexed to solve this problem. Data structures 101, right? We are going to go do the same thing for neural networks. Okay, so we are going to organize neurons. So imagine I'm trying to figure out that given an input, which neurons will have large activation. And an activation of a neuron is just an inner product of the input vector with the weights of the neurons. If I can identify higher inner products, then I can identify higher neurons. But that's again a search problem where the similarity scores is inner products. It's a similarity search problem. So I can create a data structures to solve this problem, just like I have done for the web search, right? But this time I'm not indexing web pages. This time I'm indexing neurons. All right. So here is again so I will spare you with the mathematical details, but there are ways in which you could do this. There is a whole field of probabilistic hash functions, hash tables, in which you could do this. There is a field called sublinear algorithms, in which you could figure out what is high similarity without doing all the work, right? I mean, just like how you will do search or near neighbor search. Can this query be faster than matrix multiplication? The answer is yes. And as I mentioned, this is like about 7-8 years of work. It's not like 1 year of work where you get an idea and it will work. We have figured out a way, how can I really make this whole process efficient? Again, I haven't shown you the algorithm yet. I'm just going over skimming the details. Let's go over the algorithm. All right. So here is how we are going to train a neural network. Okay. We'll initialize the neural network. So initialize neural network with random weights. Now these neurons, which are essentially a weight vector, right? So every neuron is just a weight vector. I'm going to take these neurons and reorganize them into some sort of a hash tables. And these hash tables are designed such that collisions, or if you hash is a fingerprint, right? So you'll take a fingerprint of a neuron and put it at certain location based on your hash function, right? And let's say that I know this technology, I can do efficient inner product search in this very easily, right? And I'll show you how. So imagine you get an input, which is, let's say, an image of a cat. Now everything is a vector. So let's say you get a vector. Now you will compute the fingerprint of this vector or a hash of this vector. And let's say the hash goes to location number 3. So the hash value is 3. Then you're going to say, well, I'll only go to location number 3 and I will see what neurons lies as location number 3. In this case, it will be 1, 2, and 5. So I'll only pick 1, 2, and 5. Now this hash function is designed such that hash collision is an indicator of high similarity or high activation. So just by a hash computation and a memory probe, I have better than random idea of what neurons are likely to be active on this input. And I'm only going to pick those neurons. So when I pick this neuron, I will compute activation for neuron 1, activation for neuron 2, activation for neuron 5. I will not even touch 3 and 4. Now I have a sparse vector where these 2 are 0 and these 3 are the activations that I compute. I will do the same thing for the next layer. And I'll get few more. Now, if you look at the process, convince yourself that you are taking an input, computing some fingerprint of the input, doing a memory probing, and you get the sparsity pattern of the network for that input. Okay? Now, once done, you will only feed forward on this sparse network and backpropagate for this input. Remember, it will be different for different input. If you give me a different input, I'll get a different sparse network. But for every input, I'm only going to feed forward here and backpropagate on these parameters. Now, once I backpropagate the parameters, I need to update the parameters. So let's say I updated this neuron, this neuron, this neuron, this neuron, and this. I can again go and reinsert them in the hash tables. So now I will reorganize them in the hash tables. So this is my, this is my sparse network. Then I backpropagate and restructure the memory. So maybe initially 3 now goes there where it was somewhere else. Now think again, all the work done in this process is of the order of active neurons rather than the total number of neurons. I'm not even touching the neurons that I don't need. So if this picture looks like this one, then it's not very useful because I'm only saving 2-3 neurons and doing a lot of work in hash table. But if the picture is like a billion parameter network and only 1,000 neurons, then the whole world is going to be very different. There is one bonus that we get here. We can do data parallel gradient descent. So remember, gradient descent is not parallelizable. If I made a mistake on an image of a cat, I need to first update all the parameters to even know what my errors are on the image of beer. Okay? But in this case, let's say if I use more or less an exclusive set of parameters for this image and a different set of parameters for this image, then I can update them in parallel. In fact, there is a whole theory of this. It's called the theory of Hogwild, in which it says that even if there is some collisions in the parameters, so long as the norm of those collisions is small, it will work. Now, if you want to ask what is going on here, and like this is a summary of my past 6-7 years of work in hashing. I mean, generally when we study, data structures, there is a query and a database, right? And then there is a search problems. But I want to think of them as a statistical problem. So let's say you're given a query and a database, and you want to sample an element with some probability. Sample an element from a database with a probability which is a function of a query and the element. So let's call it some kernel, like a similarity kernel. If you want to sample this, remember it's an order and sampling cost, because you at least have to compute, n is the size of this data set. You at least have to compute this kernel for all the element in the database to be even able to sample, right? I am sampling k elements with P1, P2, P3 up to Pk probability. That requires at least order k work because I need to know what P1 to Pk is. But it turns out, and this is the result that I've been heavily involved in the past 6 years, there is a randomized data structures that can do it in roughly order 1. The interesting part is I don't even have to compute this for every element in the database. It's the process itself that guarantees that the sampling will be some function of this kernel that you like, and you can compute that sampling probability. And what that means is, I think it has a huge consequence for statistical sampling and estimations. So if you're talking about like adaptive dropouts, which is the algorithm that I showed you, right? It's a sampling algorithm, sampling neurons efficiently such that active neurons are likely to be picked. You can show that it's equivalent to some form of adaptive dropouts. But you could use this also to speed up gradient descent. You could use it as a kernel density estimator. You could even use it to compress the search algorithms. And in fact, there is a recent work where we showed that this is a differentially private way to do a lot of machine learning. You can even translate it into a differentially private sketches. All right. So as a part of the startup, we are also like materializing, because I don't think there is a software stack out there in the world that runs without matrix multiplication. And this is why we are building this software stack in which, we are materializing this algorithm into reality. So we are writing everything in bare metal, let's say software. We are writing it in C++. We don't use any single libraries. Everything is written by us. And it's the algorithm that I showed you. And I'm going to share some result of how fast it is. It works on laptops, ARM and x86 processors. We actually can train 10 billion parameter networks on a desktop with this software package now. And we have a sparsity knob, and I'll talk about what are the consequences of those sparsity knob. But here are some of the results. So this is a Kaggle recommendation, an Amazon 670. It's an extreme classification data set. And here is a comparison. So this software package that we built, this is in blue. And there are two kinds of models that we are training, 200 million, which is a smaller parameter model, and 1.6 billion parameter model. We train it on Apple M1, Intel Xeon. These are like old generation processors. And this is NVIDIA A100, the fastest GPU out there. The thing to note here is as your model size blows up, your GPUs will fall short of their memory. And you will need like 4 NVIDIA A100 to even train this with large batch size. Things to note here is that this gray line is the most optimized TensorFlow or PyTorch, whatever you want to call it, package on that particular, recommended on that particular hardware. And this algorithm that we talked about, it's order of magnitude faster. Remember, it's not like 100 parameter network. I mean, if you have 100 or 1,000 parameter network, you are better off with the usual packages. But these are like million to billion parameter models, very real. And you can train them faster, even faster than on GPUs. And in fact, it's not just the time per epoch, but you can also look at my wall clock time with accuracy climb. And you'll find that this model on CPU even outperforms GPUs. So this is a result that is quite exciting. You could also do sparse inference, right? So remember, there is nothing that stops us. So even the forward propagation is fast. So both the forward and backward propagation is sparse and fast. There are some tricks needed because you cannot be too approximate during the inference time, but you can actually make this even faster than, Intel's OpenVINO and, like even using GPU acceleration, you can get much bigger acceleration on small, medium, and large kind of models for text classification. So this, to me, this is exciting because if you look at what the existing packages are, they are great for prototyping. The reason why machine learning has accelerated a lot is because if I have a hypothesis in mind, I just have to say import TF at TensorFlow. TensorFlow will write down that hypothesis and train, and it works for me. But it's not good for, like, first of all, like a production ready model. The other thing is it doesn't allow me to explore the whole resource quality trade-off. I'll talk about that in a while. But for example, if I want to answer a question like I want to train a model in a smaller carbon footprint, or I want to train a model with like less computational resources, or maybe on a CPU, I don't think these packages have answer to that. And it turns out that there is no alternative to these packages. And the problem is not the packages, it's the fundamentals. And fundamentally, there is nothing that the deep learning world knows other than matrix multiplication to accelerate AI. PyTorch, TensorFlow, every other AI package out there converts your instruction into a sequence of matrix multiplication and then hit it with matrix multiplication hammer. And I think once we get this sparsity-based alternative, we can explore an interesting landscape. So here is, so I've called it like a sparsity knob. So PyTorch, TensorFlow act as 100%. Now, if you don't believe this, do this experiment. How many of you know what is a dropout is? So go with your favorite package, PyTorch, TensorFlow, tune the dropout to 1%. That means you are throwing away 99% of the computation. Don't worry about the accuracy. Train it. The model will be slower than training the full model. Why? Because the way dropouts work, the way it is implemented is they'll first do the matrix multiplication and then hit it with a mask, which is 99% sparse. And that should actually be an eye-opener that you are doing 99% less computation. Forget about the accuracy. Your models will still train slowly. It will still consume all the resources and it will not get you. There is no way to make it faster with 99% dropouts. Whereas once you use this kind of a package, you can explore the whole spectrum. In fact, for this data set, we realize that 3 to 5% sparsity is enough to get even slightly better accuracy. And that also naturally translates in the carbon footprint. So if you train a Roberta model, training that, and if you compare the carbon footprint, it's like burning 1,000 big light bulbs. Whereas if you use sparsity, you can get the same accuracy in an energy of an LED. Right? So both compute and a carbon footprint, and to navigate this trade-off, nobody will help you, or especially if they are all dependent on matrix multiplication. And this is some of the fun of doing this work is now not only you can develop this package, but you can navigate this whole spectrum very efficient. All right. So I mean, I didn't plan for this, but this is another work where we compressed some of the large DLRM models by 1000x, which was in the MLSys work. But I think in favor of time, I would like to conclude that I think this is the most exciting time to revisit algorithms and data structures for deep learning system. So this is what I tell all my students. See, if I give you a problem and say, make it 1.5x to 2x faster, what do? You take the same approach, you roll your sleeves, use all the tricks in the textbook, you'll get 1.5 to 2x. But so when someone comes to you and say, well, I want 10x, 50x, 100x, otherwise it's not cutting it, you have to go to the drawing board. You cannot use the existing framework to get 10, 50, or 100x. And what is interesting about, what is fun about doing research is we go to the drawing board and revisit everything. Say, okay, when you go to the drawing board, take out the matrix multiplication and say, okay, what else? And I think this is a very exciting time because there is a dire need for that 50x, 100x. And that this is basically to meet the exponential demand. Again, like, see, all quantization, everything, they are constant factor improvement. The demands are exponential. A constant factor can never meet an exponential demand. To solve an exponentially growing demand, you need exponentially better algorithms. And I hope that dynamic sparsity seems a very promising approach because you're not compromising on the model size. Low rank compromises on the model size. Static sparsity compromises on the model size. Even quantization compromises on the model size because information theory only cares about the bits. But dynamic sparsity doesn't because your model is still as big as it can be, yet efficient. And again, like there's a perfect time of innovation even in the software stack. So with that, I'll conclude and say, obviously most of the hard work is done by the team. And with that, I'm happy to take the questions.
Hello, sir. Thank you so much for the excellent talk. Sir, one question that I have that in the hash table approach, you said that you dynamically update the neurons. Here, sir.
So dynamically update the
basically neurons mapping, I can say, in the hash table. So how you dynamically update it? Because it seems like once you fix the map, how you are dynamically updating that?
So the nice thing about hash tables, the reason why we like to work with hash table is, so let's say now you have 5 and 5 have updated significantly.
Correct.
So so deletion is just like addition, right? You re-add 5 and delete the old 5.
Okay, but this mapping of 5 only to the hash.
Yeah. So the way
the
way this work is to create this data structure and specifically with hash table, just like you're computing the hash for searching, you compute the hash of this neuron to know which location it goes. Right? That's how you do the insertion.
Right.
It's like a hash table insertion and a hash table search. So once you do an insertion, 5 was at fingerprint 3. Let's say 5 is updated and now it's at fingerprint 2. All you do is you delete it from 3 and add it at 2.
Okay, yeah, got it. And,
I mean, it's hash table. So one thing is nice about hash tables, and again, like I wouldn't have shown you if it was like a complex data structures. This wouldn't, again, like you can still probably make it work, but it will be another job. But hash tables, parallelizable, distributed system friendly, everything is nice about hash tables. So insertions is also very easy. You can even rebuild the hash tables if you want after a while.
Right, sir. And last question that I have is, because you are masking out a set of neurons and only focusing into certain neurons for a particular input, I'm assuming that mask is always not optimal that you are using.
Okay, can you come with the last part? Sorry, what is that?
So basically, I'm saying that the neurons that you are using, the set of neurons you are using are probably not optimal, let's assume.
So I'm not using any mask here.
Not masking. Okay, so a fixed set of neurons you are using for a particular input.
Oh yeah. So a few things. This is an approximation, right? And why does this work? So there is a lot of redundancy in the neural network anyway, right? So for example, when people say precisions don't matter, why? Right? Because Once you know that there is a nose, you don't need to know if it's nose with 0.99 or 0.97, right? And there is a redundancy. So let's say if you miss nose, but you detect eye and ears, you still can say that it's a face. How many things in this world has eyes and ears and no nose, right? So machine learning thrives on the redundancy of information. And that is one of the reasons why low precision works, any kind of approximation. I mean, think about SGD, right? Why SGD works? Nobody questions SGD. Have you ever questioned SGD? Like there are billions of samples and I'm imagining the gradient of a billion of sample with just 2 or 3 samples, and that's good enough. I mean, that's the crappiest approximation ever, and it works, right? And that is one of the reasons why it works is because there is a lot of redundancy in neural network. And this is also why this approximation.
Right, sir. My question was that with this approximation, have you seen as such accuracy drop with respect to state of the art billions of parameters model?
So, yes and no. We have seen all 3 regimes. So we have seen where the accuracy improves over the state of the art, because this adaptive dropouts you can show is also a regularization, right? We have seen most of the time we see it reaches the same accuracy, maybe with slightly more epochs. Rarely we see the drop in accuracy, but then it's always a subset. You can always tune the sparsity to be slightly higher and you go there. So if you look, I mean, I don't want to, we have this knob, right? So if this knob is set very low, you will see a drop in accuracy. If this knob is set to 100%, you get the same accuracy. In between, you can get better accuracy. Generally, what we find is that this area is where you get more or less the same accuracy, at least or even better.
Right, sir. Yeah. Thank you so much.
Thank you. Hello. Thank you, sir. Thank you, sir, for that.
Yeah.
Sir, this side.
I was waiting. So
Sir, this side.
Where? Which one? Can you raise your hand? Which
Yeah.
one? Yeah, okay.
yeah. So in the results section, you presented the performance of smaller models were like much more effective than the larger models. Like the smaller models was like 10 times more effective than the standard method, whereas the larger models were like 2 times more
This one?
accurate. Yeah.
Yeah, so these were the 3 models that we use for text classification. And again, as you can see, that, it's pretty much also consistent here. And I don't know what is, there is something about this medium model that it even makes OpenVINO much faster and GPU also to give you good gains. But with us, it was like 83x. So it's always the thing to note here is that this is much bigger than this. And OpenVINOs is like Intel's way of quantizing and pruning to make things faster. But
Well,
yeah. Was that a question?
Yeah. Like, is there any correlation between the size of the model and the efficiency of your method?
Yeah, I'm not entirely sure. It also depends on the task, right? So for a given task, a small model may perform well, medium may perform well, and large may perform well, right? I mean, and then depends on, because see, in deep learning, 2 models are as good as like they're completely different too, right? You don't know how they behave.
About the like efficiency, like the speed, like.
Yeah, so I mean, again, like I don't think there is a trend that as you can see, there is no trend here. Yeah, the largest one gives 6.7 and the medium one gives 83. Right. So it's hard to nail down a trend, but generally what we have seen is the larger the model is, we see good gains.
Okay. Thank you.
Hello, sir.
Thank you, sir, for the great talk. It was like I enjoyed it a lot. So I had a question about the size part. So you mentioned that the size of the model has to be large enough for to get good results.
Large enough, yeah.
So yeah. So there was this paper that came out in ICLR a few years ago. It's called the lottery ticket hypothesis, where they randomly initialize large dense neural networks, and they're able to find these sub networks which when trained in isolation will give you near the same test accuracy as the original one. So how does this compare to your approach of using dynamic sparsity?
Yeah, so first of all, lottery hypothesis is a static sparsity. It doesn't change the sparsity pattern. Okay. It only uses a fixed sparse network. So it obviously goes a little bit against the scaling laws that you don't need that many parameters. Second is to train lottery hypothesis, you start with a big network. So you still train it slowly. And once you have figured out the sparse pattern of the network, then you might be able to train it faster. Also, I don't think lottery ticket hypotheses actually work well in this kind of recommendation settings. In fact, there are many settings in which lottery ticket hypotheses will fail. So that's one of the reasons why people are also like little, rethinking lottery ticket hypotheses, because on some data set it worked great. And in fact, it was a great revelation that you can just restart with those sparse network as they were before and get a very good accuracy. But I don't think it generalizes very well to a lot of data sets. Plus, it's also static sparsity, right? I mean, if that is true, you could even do this on the lottery ticket hypothesis generated sparse network. So you start with that network and say, okay, now my neural network is that network. Can I make it even sparser? But we haven't tried that, obviously.
Okay, so thank you. That answers my question.
Hello. Thank you, sir, for the great talk. I had one question in that step 3 only. Sir, here when you were we were initializing hash map at 3 to be 1 to 5, at the starting, it is a random initialization or it is some smart trick to be used?
That's a great question. You can do smart thing. We do random right now. We just use random initialization and we hash them.
We are learning over the backpropagation.
So hash table creation is part of the initialization. That's the time when you do the work to create the data structure. But that's like you could be smart there for sure.
Thank you, sir.
Thanks for the great talk. So I have a question that is, I mean, the difference I think with the recent like model pruning literature is that we get a final compressed model with the model pruning techniques. But here I think it's specific to the inputs that you're using during the training. So during the inference time, what is exactly done? Are the inputs mapped? I mean, do those become the keys and then the respective neurons get activated?
So the input time is a great. So first of all, we are not doing compression here because the model size is not compressed. Pruning gives you compression, but again, like compression goes against the, like you will see some drop in accuracy very quickly. During the inference, we more or less follow the same thing what we do. So if you think about it, our forward pass itself is sparse. So even the forward pass is faster, right? Now, the one thing nice about this approach is, so existing work is like I train a network, then I give it to someone else, and then someone else now looks at the network and say, okay, remove this, and does the pruning. There's not much scope here. What we are doing here is we are telling the network, hey, look, during the training itself, that's the approximation you are going to get even during inference. If you made an error in that, go fix it. I don't know how you do it. Fix it with back propagation. But that's how we also do the inference, right? So that gives us a room to even correct the approximation during inference. So that is one of the reasons why we have even seen 300x on some of the real customer problems with for inference. But the way inference is done, coming back to your question, is very much like this. That you take the input, you hash the input, you only pick those neurons, and then the final layer, whatever neuron you get the active, you do argmax on that.
I see. So what's the size of the hash table which is used? So for classification, is it like number of classes or?
So the number of classes shows up here, right?
Yeah.
So if let's say this is big, like an extreme classification, then yes, the hash table we use is for extreme classification. But this depends on like whatever the size of the network you want, what is your embedding size and stuff.
Sorry, I like number of keys in the hash table. What's that size?
Yeah, that I actually, I hid a bit of technical details there, but there's something called a KL parameterized hash tables. So that K and L, generally the number of keys are 5 to 6, some sort of a winner take all hashes that we use internally. And our hash table size are something around 2 to the power 20 or something around that. But I mean, again, like we don't worry on CPUs, we don't worry too much about memories anyway. But these systems are like, it has a slight memory overhead of hash tables, but otherwise it's fine.
Okay, so similar inputs get hashed to the same key and then the
that's the property of LSH, right?
Okay.
So similar input
Yeah.
maps to same keys, and this is a lot is known about this, and yeah.
Thanks.
Hi, thanks for the exciting talk. And so my question is regarding like, does the sparsity hypothesis holds for all types of tasks and inputs? Because it seems like we are kind of constraining the capacity that is assigned to individual inputs, and there might be some queries which are more complex than simple classification, image classification task. And even within the task, it might be more complex.
No, that's a great question. Are there certain kind of inputs where sparsity may not matter that much? The answer is yes, especially if the network is small, sparsity don't seem to matter. But if the network becomes big, you always see sparsity. So this is something experiment that we did with GPT-3. So there are 3 sizes of GPT-3. The smaller size GPT-3 is about 80-90% sparse on any input. The larger size GPT-3 is 99% sparse on any input. And when I say sparse, means completely sparse. And we are not enforcing any sparsity. We just ask GPT-3 to go and do the inference, and you just look at the activation, the 99% of the activation will be 0. Not in the final layer, it's just even in the intermediate layer, it will be all 0. So that, and if you decrease the size of the GPT-3, it will become 95, 90, 80, and there will be a size when it will become dense. But that size is basically, people don't use that size anyway because it's hard to train.
So is this number an average? Like, does this 90% sparsity holds for all input, or there can be some inputs which might require more neurons to be activated?
See, it's machine learning and deep learning. It's all going to be very dependent on the data and the input, right? What I want you to focus is that we have created this knob, right? For some problems, where is the sweet spot, right? Ideally, it's just like how sorting works, right? In the worst case, it's n log n. So worst case, it will be probably somewhere here, or maybe here 50%, because 50% dropouts always win, right? So this is the worst case scenario, but there are a lot of problems that you can solve here. In fact, what we are realizing is for most of the problems that we encounter, the sweet spot lies somewhere here. But definitely there will be an outlier case for which this will not work, if you're asking that.
Right, yeah, so that was the question. But yeah, so your model can allow for like dynamic sized sparsity also, so that percentage can change.
Yeah, so the way we have designed this engine is use pre-specified sparsity is a norm. So you can say that I want to operate at 1% sparsity or 20% sparsity. Or maybe, so this is basically 5%, 10% or 20, whatever knob, and it will give you the best accuracy in that sparsity. And we often see that the best is for larger networks is always less than 1 or 2%. It's good enough. For small networks, maybe 5, 10. You never have to cross 30. That is what we have seen.
Yeah. Okay, thanks.
Hi, good morning, sir. Rahuli. You were talking about choosing the features in such a way, as in for particular categories of objects, we are only choosing a particular set of features, right? And
or rather neurons, okay?
Neurons, yeah.
Let me show you this plot, yeah. Okay.
Yeah, so particular sets for particular objects. That's the first thing. And the second thing is, you said when we are training a model using all the neurons, all the features, it's taking a relatively less time than neurons, a few features less than that, right? Now, when we are training it using all the features, and we are only using a few to in order to try to categorize a particular object or trying to understand what that particular sets of features interpret, the accuracy is obviously going to be affected.
So before we put that, so we are not generally, so the observation that we show here does not come from the fact that we are trying to force anything, okay? So let's take this dense network. Let's take the standard way of training neural network, right?
Yeah.
The standard way of training neural network, if you try to see what are the updates, so there are, let's say, 1 billion parameters here. Now you plot all those billion parameters on the magnitude that they have been updated. You will see that 90% plus parameters are updated with 0.0001.
Okay.
And I'm not doing anything. Now you will go to another package and say that, well, I have quantized it to 8 bits or something, which is what NVIDIA will do. And you will see that those updates are anyway washed away.
Okay.
Right? So now, even in the best package out there, what is essentially happening internally is the algorithm does one thing, but what gets affected is only 1,000 parameter out of 1 billion. And I'm just making up some numbers here, but it's on the order of that thing, right?
Yeah.
So what does that mean? That means that we are doing a lot of zeros and we are paying for it.
So those are practically of no use to us.
Yeah, they are wasteful.
Okay.
So this is a smarter way of like eliminating that waste.
Okay. Okay. Thank you.
Okay, I will take one last question, I think. I know we are overshooting time, but it's the last one.
Thank you for the great talk. So my question is this kind of approach robust towards adversarial training, where we would like to, map different kinds of features to the same class maybe, but different kinds of activations are there for 2 inputs, which should be mapped to the same class, but have different feature set.
So great question. And I'll take this liberty to also talk about some of the research direction we are thinking. So now that, again, this is what we constantly think about in our lab and otherwise. Now that we have a different way to train, which is with sparsity. What are the consequences? One question is this new way training more robust? In our opinion, yes, because if you think about adversarial attacks recreates the gradients and then use that gradients to recreate an input. But then this is like adaptive dropout. So it's already regularized to some extent. And nobody knows which neurons the algorithm will pick. Because you only have access to the neural network. You don't have the access to algorithm of how I trained this. Which neuron was picked for which input. Right? You can probably still figure something out if you have enough access to the thing. So we have a belief that this is more robust. Second kind of research problem is like, is this less forgetful? I think yes. I mean, there is something called catastrophic forgetting in neural networks. If you train it, the neural network on a different distribution, it forgets. But if I can do data parallel training, like the cat and the bus can be trained in parallel, I don't think that this will forget if the data distribution shifts slightly. And there are a host of problems that we are thinking about. So we are like working a lot on this. I mean, I used to call it that we do like hashing, sketching, and this thing on steroids. So we just take all the algorithms, just like mix and mash them up, still works. And now we ask a question, okay, we have created an interesting stuff here. Does it has all the bad properties that is there, or what could go bad? But that is all a very good and interesting research direction. And if you're interested, definitely shoot me an email.
So we should
Thank you. Thank you. Please. Oh, thank you.
So I have some announcements to make. So we will quickly go for a small coffee break and come back in 10 minutes. Okay. The next talk is also very interesting in the same line, a very practical talk. So please come back early. Next, all those who have not given their travel gun, please give it before lunch. Next is there will be a photo session just before lunch, and we'll have a group photo done. And also from 1 o'clock, the mentor session starts. So there will be small groups of 10, 12 people, and there will be mentors and rooms. Anirban, where are the rooms? Rooms are? Yeah, rooms are there, and everybody will be allotted to a mentor. So you should follow that instruction and go to the mentor. The list will come out soon. Okay, fine. So now up for coffee.